Alright, so moving along in chapter 15, we're going to look at directional derivatives and the gradient. So first off, we're going to determine some directional derivatives. Then we're going to calculate and interpret the gradient and relate the gradient to level curves. So to start off, let's do just a quick review of what we've already done with derivatives here in 3 dimensions. So we've looked at partial derivatives, and those partial derivatives tells us the rate of change in either the x direction or the y direction. So we have our standard Sarah cut and paste error here. Let me get an annoying color here to write that we're talking about in the y direction there for our partial derivative with respect to y. And another way to think about these that we didn't talk about in those particular sections is that when we're moving in the positive x direction, that is the same direction as our little unit vector that sits down in the xy plane, 1, 0. Same for our partial derivative in the y direction. That's moving in that positive y direction, which goes in the same direction as our little unit vector j, which points towards 0, 1. So what we'd like to do is not just be restricted to looking at how this function's changing going in just those two directions. We'd like to be able to, or even like we did in the last section where we were looking at, along a particular path. So we want to say, okay, if I'm standing at a point, I want to be able to go off in any direction that I want and know exactly what my rate of change is going to be. So that's what we're going to do here. We're going to look at the rate of change in any direction that we want to go. So again, that's our goal, to be able to find the rate of change at the point AB going in any direction. So we're going to look at this like we're going to have some little vector here, vector u, and it's going to sit in the xy plane. And this is going to tell us the direction that we're going to want to leave on our surface. So for example, we're going to have some sort of surface up here. And we've got some point on it, maybe over here. It's going to be AB and then F of AB right there. And we want to go in this direction of U. So let's maybe see if we can copy that. And let's see if we can paste that right there. Yay. Oh, I grabbed too much. Bummer. Well, we'll see if I can draw that direction there. And we want to be able to go that way, that same direction as our vector u, and know what our rate of change is and how steep that is. What's going to be our steepness there. So a couple things to notice on this is that we've said that u is going to be a unit vector, so its magnitude is 1. This is really just a nice convention for us. We'll see why it's a little bit helpful, but it's really going to be nice for us to have that magnitude of 1. And honestly, we only need the direction that we're going, so we don't need it to be, a certain length, long or short. So it's just going to be easier for us to say, okay, let's figure out what direction we want to go, and we're going to use the unit vector that goes in that direction. So we're going to take a quick look at a 3D function that I have graphed on a 3D grapher and look at the directional derivative at the point 1, 1 going in the direction of the vector 1, 1. So let's go over here. There we go. So I graphed that surface that I said there. And that one was z is equal to negative 1/2 y squared plus 3. And it sort of kind of looks like a tent. It looks basically like a parabola, and it's going to go off infinitely along the x-axis there. And so I've got things kind of set up here, and then I've got a direction vector that I'm going to put in. So the idea here is that we've got our point, there we go. We've got our point 1, 1, and what we want to do, whoops, that's not where we are though. We want to go to 1, 1. There we go, point 1, 1. And we want to go in the direction of the vector 1, 1. So there, ooh, that's a really good shot of that. So there is that direction that we want to go through that point, and we're looking at finding what that little tangent line is there at that point. Okay, so that's the idea of what we're doing. So again, this is another way for us to create different paths along this surface and to have it be a lot more general than what we were looking at in the last section, where we really had to have those curves defined by some functions. Here we just need to know what direction is it that we want to go, and then we can slice our graph along that direction. So it's just going to give us, again, another way that we can do this. So let's take a look back here. So, what we can do is we can change that vector. So here, if I change the vector, notice it's changing my path, it's changing my tangent line. Can't quite see that it's changing the tangent line, but here we go. Maybe if we do that, you can see that it's changing that tangent line. Cool. We could also change the point and move in that same direction, but along different points. So we can see that. Fun. Oop, then I get it spinning. Okay. So what we found here is a directional derivative. So this guy right here, this is our directional derivative of our function f at AB. So this is telling us the instantaneous range of that function when we move in the direction of our vector u away from our point. So we're going in the direction that u points away from our point. So our definitions for this, the first one is our limit definition, and I mostly put that there just so that we know that yes, this limit definition exists. We're going to look at how both the a and b are changing as we move in that direction. And again, like with all of these, there's a lovely proof of this in the textbook if you want to see how we get from, this fantastic limit definition to our actual, useful definition that we're going to use to physically find these directional derivatives. So if you want to, see how that's walked through, that is in the textbook. I don't feel like that's a good use of our time here. So we'll go straight here to this second part, which is our really most important part here, because this is how we're actually going to calculate those directional derivatives. So let f be differentiable at our point AB, and let u be our unit vector. And it's got its two components, and it's in two dimensions. And again, that's what we want it to be because it's just sitting in the xy plane. And the directional derivative of f at AB in the direction of u is the dot product of a vector made out of our partial derivatives at that point. So these are the partial derivatives. And because I'm picky, there we go. And here's our direction. And we're finding the dot product between that directional derivatives, those directional derivatives at that point, and our direction. And so this is going to output a number or an equation that we can use to find the slope going in whatever direction we want to go in. Or from whatever point we want to go from if we know the direction that we want. Okay, let's take a look at an example here. Okay, yeah, I don't want a bright red pen. There we go. So say we're given a function f of x, y, and it's equal to negative x squared y, and we want to find the following directional derivatives. So we want to go through the point 1, 1 and in the direction of I, and this is going to be a quick one here. So I is 1, 0, that's in the x direction, the positive x direction. And we'll say positive x-axis here. Okay, so our partial derivatives, oops, nope, we're fine. Our partial derivatives are negative 2x, partial derivative with respect to y is negative x squared. Our partial derivative at that particular point, again, so that's plugging in our point. So we get -2, and we get -1 squared. So we get -1 there. So our partial derivative at that point, or partial derivatives evaluated at that point is the vector -2, -1. And so our directional derivative in the direction of I at the point 1, 1 is going to be that partial derivative that's plugged in, and 1, 0. And so the thing that I want you to notice about this, because we're going in the x direction, that y component zeroes out. So this is just going to look at what's happening in the x direction. So essentially what happens is that we get the slope in the x direction, which is what our partial derivative tells us. So the nice thing about this formula for finding that directional derivative, it still gives us the same partial derivatives that we had a couple sections ago. But again, the idea is what this is giving us is if we are standing at that point 1, 1 and we go in our direction that's parallel to the x-axis, we're going to start out at a slope of -2. Right? So if we want to go through the point 1, -1, 3 in the direction of v is equal to 2, 1. So again, we need our partial derivatives evaluated at that point. It's again our directional derivative at AB. Oops, you know what AB is. AB is -1, 3. That's going to be the vector that we get from our partial derivatives evaluated at that point. And then dotted with, we need a unit vector. I don't know if this is a unit vector. We better check that first. So that's something that we're going to need to be careful about because sometimes they will give us vectors that are not unit vectors, and v is not a unit vector, but we can turn that into a unit vector. We've done that before. If we multiply by 1 over the magnitude, now we've got a unit vector. All right, cool. So now we're finally ready to go here. So we get -2 times -1, which is 2 in our partial derivative in the x direction. Our partial derivative in the y direction, we're going to get the opposite of -1 squared, which is going to give us -1. All right. So now we can set up this vector. We're going to get 2, -1, and then we're going to dot that with 2 over the square root of 5, and then 1 over the square root of 5. So our slope is going to be 4 over the square root of 5, and you know what? Oh my goodness. I left something out, didn't I? Ah, yeah, there's a y there. And it doesn't matter for the first problem. Phew, thank goodness. And I noticed it here before it mattered. This is why I should always look at my notes. Because that should be +6, excuse me, +6. Maybe you caught that, hopefully, before I did there. So that should be 6, so that's going to be 12. There we go, plus. And then we're going to get -1 over the square root of 5, so that's going to be +11 over the square root of 5. I really don't mind if you leave answers this way. Textbooks and things like My Math Lab are often picky and they want you to rationalize the denominator. I really don't mind. Either way is fine with me. But again, this is giving us our slope at that point, and it's giving us that direction. So it's telling us, whether we're going uphill or downhill. So if we leave from that point in that direction, we're going to be going uphill, and that's going to be our slope. I think I will stop this one here, and I'll start up a new video for us for the gradient. So if you wanted to review either of these two alone, you can do that. So we'll do another one here for the gradient.